So these are really the 4 pillars under the project. It involves agency collaboration with the different government agencies as well as a host of industry collaboration. In fact, after we had this project, we also launched the Singapore Cybersecurity Consortium, and that provides a very good umbrella for engaging not only with one company but rather a consortium of companies. And also we are trying to, this is just mentions just one thing, a new module, but we have also launched a bachelor's level degree program in information security. So apart from a master's level degree program, a master's level degree program was launched in 2006. So that's quite mature. But in 2015, after this project started, we have also launched a bachelor's level degree program at NUS in information security, because this we see as a fairly critical need. Right, and of course there are publications, tools, academic collaboration as in any other research project. Okay, so at this point maybe I'll just play 2 videos. They are very short videos, and the voiceover is actually done by my students.
This is Bob. Bob receives an email with an attachment. This attachment is a document which Bob...
I think this is too much.
This is Bob. Bob receives an email with an attachment. This attachment is a document which Bob can open in the program. Once he opens the document, he finds that his credit card details have been stolen. Now, because of a vulnerability in the program that Bob uses to open the file, his computer gets compromised. As security researchers, we analyze such programs to understand whether they can be used to compromise a computer. This is called automated vulnerability detection. We can distinguish 2 main techniques. Our tool Hercules is a very effective white box fuzzer. Here we demonstrate how it crashes Acrobat Reader. Our tool EFL Fast is a very efficient black box fuzzer. In this fast forward, we demonstrate how it finds the first vulnerability in under 10 minutes. Our tools expose vulnerabilities in large, well-known programs that take complex files as inputs. And the best part is, it works directly in the program binary. Our fuzzers are both more efficient and more effective than state-of-the-art. Our tools have been used to find several severe vulnerabilities in widespread programs. Fortunately, these vulnerabilities have all been patched by now.
Okay, so this was just a 1-minute video to give an idea about the vulnerability detection.
Heartbleed is a security vulnerability that affected 17% of secure internet web servers. It allows attackers to steal valuable data through insecure internet communication. The vulnerability is caused by a bug in OpenSSL cryptography library, and our tool, Angelix, can fix this bug automatically. Angelix uses program analysis and constraint solving to answer 3 questions. First, where to fix, that is to localize the problem. Second, what to fix, that is to understand the problem. And finally, how to fix, that is to solve the problem. Then it applies the synthesized patch to the buggy library implementation. The vulnerability is now patched. If the attacker attempts to steal the data, he will fail.
So this is again a very short video on the patching. So this just gives a very quick idea about the kind of techniques we are talking of, mostly in the domain of vulnerabilities. So we might think that, okay, who would be interested in this kind of suite of techniques? In relation to this, I can mention this DARPA Cyber Grand Challenge, the CBC, which was just concluded in 2016. A lot of us, I'm sure many of the students here would have participated in hackathons. This is the first machine-to-machine hackathon, okay, where the machines are trying to beat each other. And so they are trying to hack into the other team's software, and then the other team's software is trying to defend itself. So this was the very first machine-to-machine hackathon. It's a very important challenge from the point of view of ICT. This is a very, very important challenge undertaken by DARPA. And essentially what it does, if we think about it, it's really automation of security. So all the teams participating in this, they are really trying to defend their software, and they are trying to employ techniques like vulnerability detection as well as hardening. We are located in NUS, so we cannot theoretically participate in this DARPA Cyber Grant Challenge because this is only for universities in the US. But we participated by teaming up with one of the teams because the fuzzing software that we have, this one of the teams found that this is the one that would be much more useful to them. And then accordingly, they used it and got very, very good results in the vulnerability detection. So this is just the prelude about the techniques that I'll talk about. Okay, so the techniques that I'll primarily talk about, given the time that I have, would be in fuzz testing. So let me focus on that. This fuzz testing was course, being a semantic technique, this can be more inefficient. So I'll tell about some results just to show the application of these techniques in directed search in white box fuzzing. All of us might be familiar with pop-ups like this. We are trying to use a software, maybe the Adobe Reader, and it gives you a prompt like this, that it has encountered a problem and needs to close. Of course, it is sorry for the inconvenience. And then I don't know which one we usually click. So I usually click the don't send, but there are enough number of users who click the send error report. Okay, so it's not everybody is like me, silently accepting the crash, but a lot of people would send the error report. So once they send the error report, on the other side, it's not very easy to even reproduce the crash. Just to let you know about the challenges, it's not even very easy to reproduce the crash because the crashing input, in this case the PDF file in question, is not shared to the other side for privacy reasons. Okay, so it's not even very easy to reproduce the crash. So for in-house debugging and fixing, or even vulnerability checking, you need to reproduce the crash. You might only have the crash location and possibly a stack trace. So one of these works, it's just a sample, one of the works that we had looked into in this area is where you will take a program binary, possibly some information about the crash, say the crashing instruction, and some benign input files, which is always available. If you are trying to find out crashes in the PDF reader, you always have some PDF files. And from there, automatically generate a crashing input file, which specifically visits this crash instruction and reproduces that crash. So I'll not get into the details of all of the details of the technique that we had employed, but I'll mention some of the challenges. So for these kinds of problems on very large scale software, like software which we are regularly using even today, possibly as I'm talking, you are probably browsing some PDF files or looking at some videos, so things that we use regularly, there are many, many challenges for finding out vulnerabilities. And the least of which, the very first step, is to even reconstruct the control flow of the software. Whenever we have a certain program, if we can look at the source code of the program, we assume that regenerating the control flow is trivial. For these kinds of software, since you might just have the program binary, even regenerating the control flow is non-trivial, because the targets of a jump instruction could not be known at compile time. They could be given by the values of some registers, and that they may not be known at compile time. Okay? So this is certainly one challenge that we need to overcome, which we did. And then subsequently, even after these, actually this work was done on Windows binaries. So apart from the control flow graph, the Windows binaries would have modules. So we also have the module dependency graph, which is shown here rather cryptically as MDG. Once we have regenerated these structures which capture the control flow in the program, subsequently we do this task called this concolic exploration, which is essentially the symbolic execution approach that I showed just now, where you try to cover more and more paths in the program in a systematic fashion. But then you don't want to make, the trick of the trade is you don't want to make everything symbolic. Imagine that you have a PDF file, a PDF format. You really cannot afford to make every field in the PDF file symbolic, because you would just have too many symbolic variables, and the vulnerability detection will be very, very inefficient. So we try to also find out through this taint tracking which ones should be examined further, and then subsequently we go into the crash location and generate a crash revealing input. This one single flow, this involves many, many heuristics, how to even do the backtracking, even after you have decided on the symbolic variables, how to even do the backtracking. There are many, many nifty heuristics, how to handle string variables, because the string variables create a very large search space, and so on. So I'll share some of the results. So you can see these are really experiments on real-life software at a very large scale. Even if you can reproduce the crashes within 24 hours, that's considered a fairly big win. And here, this is the technique that we had developed, the tool. This is actually a commercial. So people would pay a lot of money for this kind of a commercial fuzzer, a commercial black box fuzzer. And this is a purely white box fuzzer developed at EPFL. This is the version that we had at that point of time in 2015. These are all the programs that we tried out on. This is actually the Windows Media Player, the Acrobat Reader, Real-Time Player, Orbital Viewer, and so on. So you can see the results. I'll not dwell too much on the results, but this is just to show the kind of capabilities that are possible. I'll mention briefly about the vulnerabilities in file processing programs. This is an area that is quite actively looked into by the companies because there are lots of vulnerabilities. So this is actually showing the number of CVEs that are lodged. Every vulnerability that exists, there may not be a CVE in the US National Vulnerability Database. So you can see this is fairly large. I have the slightly older figure. I should update it with the 2017. And these are all the usual formats. So the combination that we had worked out here, I'll not again get into all of the details of the techniques. The combination that we had worked out here is that we have again a test suite. So if you are working with a PDF reader, this could be a bunch of PDF files. So through a file cracker, we will try to crack open the various fields in the file. And then we have a pool of fragments to play with. And then subsequently, we will be doing symbolic execution. But as we do the symbolic execution, it finds out what are the important fields that are required for reproducing crashes that are not even present in the existing seed files, because the symbolic execution might get stuck. And this is what we call as the crucial if statements, where we cannot make any further progress through the semantic analysis. And then we come to the syntactic analysis, let it come to our rescue. So this file stitcher really comes to know from the symbolic execution what are the fields that are missing. And it generates an appropriate mutation, which is then given as the seed to the symbolic execution. So this is a kind of a nifty combination that we had looked into. This one led to much better results, I would say. Again, these are all fairly well-known programs like the VLC player we would be familiar with. Again, the Windows Media Player, Acrobat Reader, and so on. So this one we call as just the ++. The previous tool was called Hercules because it's a Herculean effort to analyze these kinds of software. So this one we just call as ++ with this kind of an addition. So this probably gives a flavor of some of the capabilities that can be that we have tried to build in the area of vulnerability detection. Now I will switch gears a little bit and talk about one specific vulnerability detection technique that we developed. It was built on top of a very popular fuzzer which is used very widely called the AFL fuzzer. AFL stands for American Fuzzy Lop. So what we did is we just made a very small change, a very small change. The total amount of coding done by us was probably less than 30 lines of code. A very small change in it, and kept everything else the same and increased its effectiveness by more than an order of magnitude in terms of finding crashes, at least as witnessed by the DARPA Cyber Grand Challenge binaries that I mentioned earlier. Okay. So just to recap, this technique takes in a test suite. Again, there's some seed inputs if we are trying to crash the PDF reader, PDF files. And it has mutators which will generate the mutated files. And then from there, it will try to choose certain interesting inputs for further examination. So just to make it, just to show this in the fullest details, it's not very complex. The overall algorithmic framework for finding these crashes is not very complex. I can fit this into half a slide, okay? So here we are really having these seed inputs S. We start with those. And the TX, this is really the set of crashing inputs that we are trying to find. So really the only knobs that you have, the only knobs that you can tune is that once you choose an input for examination, how much time you will spend on examining it. And whether you choose, once you choose an input, whether it is deemed as interesting for further examination. So the only change we made is just in this, that once an input is chosen, how much time we will spend on examining it. And it so turns out that in the CGC binaries, they produce the crashes more than an order of magnitude faster. So that's why able to get into all of the details of what made it faster, but I'll give the general intuition. Oftentimes when we are programming, if we are a good programmer, and of course we are all talking of commercial software here, so these are well-written software. If we are a good programmer, we would have lots of checks at the beginning, like if checksum is not valid, then quit, then abort, or if this other length field doesn't meet this constraint, then you get out, and so on. So you would have lots of checks, and so there will be some very shallow logic at the beginning of the program leading to some very short paths which are exercised by invalid inputs. Okay? So therefore, if you have a semi-random procedure of just mutating a PDF file, generate another PDF file, you would generate a lot of invalid PDF files which just go through the same shallow logic, and it's not at all exploring the deep logic in the program where there would be more interesting and nifty vulnerabilities. Okay? So we try to avoid going through these short paths again and again and again by changing this assign energy function. So this is the only change we made. This was the key observation, and the results are there to see. This was published in this last year's CCS, and the results are there to see. So here you can see this is without the change. This is the normal American fuzzy lob, which a lot of companies also, there are a lot of company users of this. And this is the number of test cases plotted against the number of paths that are traversed. So this is a graph in the log scale, and I don't know whether it's visible. There are 3 dots over here. So 3 of the paths are being traversed at least half the time. Half of the time budget is going away. And here you can see double as many paths are being traversed, could be even more, and typically in much less time. Of course, it's always good to have results in academic papers, but to me what was very, very pleasant is that we also got very good online reputation, and as soon as we put up the results, there was a lot of acceptability of it, as a result of which it was integrated into the AFL mainline so that this technology is available. Right, we have also looked into other kinds of, this is the latest results just from this year in CCS, where we have tried to bring in the power of semantic analysis. This gray box fuzzing, it's really not a semantic analysis. It's really following a genetic algorithm kind of approach, which has an inherent amount of randomness in it. Randomness is also useful for getting out of certain regions in your program. If you get stuck in semantic analysis, randomness is useful for getting out of there. But we need to combine the power of semantic analysis as well as these kind of random and semi-random approaches. This is what we have done in the latest results, where we want to take the key power of semantic analysis. The key power is that it is directed. If I tell that reach this location in the program, that can be stated as a constraint, and the constraint solver can take care of it. So we want to bring in this key power of semantic analysis into these kind of random and semi-random approaches so that the technique is both effective and efficient. So these are the latest results we have, and in fact we have this has been integrated already. In fact, the conference hasn't taken place yet. The results have been integrated already into this OSS fuzz. And this has a variety of applications. Of course, we would be interested, rightly so, in the applications. So for example, when you introduce patches, you want to test them. If this was done properly, the Heartbleed vulnerability would never have been introduced. Okay? This is what we showed in our work: reaching a dangerous location, crash reproduction, and so on. Okay. So in the remaining time that I have, I'll talk a little bit about this auto-patching work. This is another capability building that we are trying to do at NUS, and this is also in this area of software engineering and software security. This is also at this point of time a very hot area. So if any student here is looking for a suitable research area to look into, this is a good hot area to get into at the right time. Okay. The problem here is extremely simple. We have a buggy program and we have some correctness criteria given in the form of failing or passing tests, and we want to produce a minimal modification of the buggy program so that it can pass these tests. Okay? So this is really the dream that we would like to achieve, and only if we achieve this dream, is the dream of automatic programming ever possible? Because of course, if we cannot even patch our programs automatically, there's really no possibility of programming automatically. So we try to divide this problem into 3 steps: where to fix, what to fix, and how to fix, as was mentioned in the video. And for some of these techniques, we are trying to use this symbolic execution. I'll just mention the key intuition and how it differs from previous genetic approaches. There were other approaches like called Genprobe, which focuses on genetic programming. So given a buggy program, it will go through generations, try to generate mutations, and try to see whether they are passing enough number of tests, and this process will go on until you hit a program which passes all the tests. Of course, this process can take quite long, and you may not get a repaired program. So in our approach, this is what we did. We tried to divide the task into these 3 steps: where to fix, the fault localization, the specification inference, and the patch synthesis. I'll not get into all of the details, but I'll just give the key intuition via one simple example. Assume that this is the program we are trying to fix. The error here is this bias equal to downsep. This is mistaken, and it should be bias equal to upsep plus 100. How can your programming environment figure this out automatically, provided you are given a set of test cases which capture your intention in the program? So maybe some of these test cases fail, and you want to make the small change in this program so that all of these test cases pass. The interesting thing to notice here is the first step is debugging, of course, where to fix, and there may be choices. But even if we know, suppose even if in our dream we came to know, somebody came in our dream and told us in our ears that line 4 is the one you need to fix. Even then, the programming environment cannot figure out automatically, because there are infinitely many expressions with which it can replace it, or even the left-hand side may be wrong, and so on. So there are infinitely many ways of mutating this, and if we just go through them one by one, this may not be a very productive endeavor. So the key intuition of what we have done, so first is of course the localization. Even if we know it is line 4, there are some techniques for that. The key intuition that we have done is that we say that, okay, this will be an expression, and I don't know what expression it will be. Let's call it x. So we just replace it with bias equal to x. And for the different test cases that are failing as well as passing, we do concretely execute it up to that point and try to see what values x should take so that the execution then leads to a passing execution. So for example, here, through an analysis of the program, I can figure out that if I go down this path, I will pass the test, but if I go down this path, I will not pass the test. So the key intuition is really this task of automatic program repair. We are converting it into synthesis of a mathematical function. So we say that this can be any function here, this expression on the right-hand side, this can be any function here. And we just call it a function f in terms of the live variables of the program. In this case, these are the only live variables. So we just say that now I have to synthesize a mathematical function, but it should be such a mathematical function that it passes all my tests. And now I can gather properties about this mathematical function by running each of the tests. So I run this test, which was failing, it comes up to here, and then I come to know that, well, from this x greater than equal to 110, this x is not any x, but it is a function of the live variable. So I come to know a small amount of property. So this is a pure intuition here. We come to know a small amount of property about this mathematical function that I need to synthesize. And from each of the tests, typically in an industrial scale software, you have a fairly rich test suite. From each of these tests, I can get small properties like this about the mathematical function that I want to synthesize. And then, depending on the components, that is the operators that can appear in the function that I want to synthesize, I can actually generate the expression. So the key intuition here, there are a number of works that we have done here. And subsequently, we have also developed some technologies which are publicly available. But the key intuition here is this task of automatically fixing your errors. This can be converted into synthesizing a mathematical function. And then from the test cases in your program, you gain properties about this mathematical function. So this was the key observation, and subsequently it has been taken up by a number of research groups. It also leads to, I will not get into all of the details, but it also leads to higher quality patches than the syntactic analysis approaches, as might be expected. And it also helps in terms of this so-called overfitting problem in program repair, because the correctness criteria is just given by test cases, which is an incomplete specification. So it can overfit the test data, so it also helps in that regard. So with that intuition, I'll probably conclude this part. In fact, this is not the latest results. I put this in quote because I didn't update the slides. So this is just the results from the Heartbleed vulnerability. So you can see this was just the vulnerability. This is the buggy part of the OpenSSL library. The only thing that caused the vulnerability is that this check was missing on the payload. The payload may be too long, and it should check whether the payload is too long. So this is the fix that is generated automatically, and this is the developer fix, where it is checking whether payload plus 19 is greater than this expression, and the fix that is generated automatically is payload plus 18 is less than. So actually, the automatic system is generating a fix which is not identical, but it is functionally equivalent to the human fix. And this is the direction we are going towards. Again, I'll not share all of the results, but this is just a sample of the capability. Okay. We also have subsequently taken this work forward in the form of a spin-off from NUS, which does this kind of fuzz testing on mobile apps, where we have also an automated model extraction from the mobile app, the Android app, and from there do automated test generation. Not only for crashes, but also combining it with manual testing, because whenever we launch a spin-off, we have to cater to number of clients. So sometimes the clients might say, we have fair amount of testing done already. Can you help improve it? Rather than trying to do everything automatically. Okay. So just to bring this part to a conclusion, so we have looked into this scalable analysis on program binaries. There are a variety of techniques, a variety of observations going into it, clustering of paths, controlling symbolic variables, and so on. And there are a variety of users. So for example, there is interest from anybody working with safety critical software. Before they procure some software, they want to run these kinds of checks on the, say, on the evaluation version, because this can be run directly on the binaries. Or people trying to do a COT system assembly. So we are working with number of organizations into transplanting some of these techniques. And one of the key observations that we had here is that apart from guiding the search, this is also a process for extracting the semantics, the intended behavior from buggy programs. Okay. More details are available from these websites. So I will very quickly mention this Singapore Cybersecurity Consortium. In conclusion, this is a consortium of 25 member companies that we have set up, that I helped set up about a year ago. This is a very good engagement platform for companies, academia, government agencies, our National Research Foundation, and also a lot of students. And that is one thing I want to talk about. So the consortium has a number of activities in training. So there is a training camp. This might be of interest to some students here. So that's why I wanted to talk about it. Also a forum, providing a forum for engagement like tech updates, a wacky day, wacky styles for wild and crazy ideas, as well as translation. So providing seed grants and creating a repository of projects, because the professors might be too busy. There might be many, many student projects which are ripe for translation, and they could be made available to the companies. So this is an endeavor that we have taken up in Singapore. There are quarterly tech update meetings. Of course, management of the intellectual property, that is a key issue, and lightning sessions and so on. One of the goals is to promote greater translation, use the repository of projects that already exist in the institutions of higher learning, IHL, and therefore provide a pathway to the companies from training to alleviate the pain points, and then finally in terms of research collaboration. And for this reason, we also give out seed grants for company university pairs. So the consortium gives out seed grants for company university pairs to team up and do projects. And we are also having these special interest groups so that there are more targeted discussions on threat intelligence, data protection, mobile security, software security, IoT security, and finally cybercrime. Each of these this is a Singapore-wide effort, not only in NUS. So each of these special interest groups is headed by a separate entity, typically a university. It could also be a research organization, or in the case of cybercrime, could be the government or a government ministry. So specifically, I wanted to talk about the Cybersecurity Camp that we hold every year. This year, it will be on artificial intelligence and security, and it will be coordinated by Don Song from UC Berkeley. So the students here, if they are interested, there is an application process, and feel free to apply. And we try to provide some scholarships to interested students for attending this camp annually. Okay. With this, I would like to conclude. Thank you very much once again for giving me this opportunity to share the developments, and congratulations once again on the new building and the new auditorium. Thank you.
Please don't go far, just stay. Thank you very much, Professor, for that very mind-blowing session. Now, it's a special moment to felicitate Professor Abik. May I now invite Professor K.P. Hewagamage, the Director of UCSA. Thank you very much, both professors. Now, before we break for tea, we have all of you, I want you to stay because we have to take a group photograph. And before that, there's a little message that I would like to convey. That is, we would not have had this event without the help of these people. That is technical sponsor, IEEE, our platinum sponsor, Cambio, gold sponsor, National Science Foundation, and the silver sponsors, Millennium IT and IFS. Now we have a message, a brief message from our sponsors. Yes, thank you very much. And before we break for tea, I would like to announce where we would have the sessions. The session on software engineering will be held at the mini auditorium, second floor. And the session on language processing will be held at the ADMTZ, that is on the third floor. And the session on ICT for development will be here. So those who would participate for that session on ICT development, ICT for development, can stay here after tea. Now, before we break for tea, I want all the registered members as well as the keynote speakers on stage, please. So can we have all the keynote speakers and the registered members of the ICTer conference here? The UCSC staff and the members of the review panel as well. Please come. All the members of the organizing committee and all the authors are invited as well. Reviewers, so I'm sure you do not want to delay your refreshments, so please come over. It doesn't matter whether you're photogenic or not. Please come. So thank you very much. I would like to once again announce the session as you break for tea. Session 1A, that is software engineering, will be at the mini auditorium. And session 1B will be there at the ADMTC, third floor, language processing. That's the session. Session 1C on ICT for development will be held at the VKS auditorium, that is here. And please be back by sharp, the sessions will start sharp at 11. Thank you very much.
So meanwhile, I would like to give some few announcements as well. The tea will be served in the 5th floor, which means that one level up in the 5th floor. At the same time, the premise is Wi-Fi enabled. SSID is ICTer 2017. So you may mind the password. All letters are simple. ICTer 17 at UCSC. ICTer 17 at UCSC. SSID is ICTer 2017. Right. Thank you.